Let's code an algorithm to implement matrix column vector multiplication via linear combinations. Remember from our definition that in order to do this operation, we need to be given a matrix A, which we'll say has m rows and n columns, all entries of which are real numbers. And we'll also be given a vector x, which has n rows and one column. Notice that the number of rows of the vector x matches the number of columns of the matrix A because the inner dimensions must agree. We say that the linear combination version of matrix column vector multiplication, where A is our matrix and x is our column vector, and we multiply those together to produce A times x, is given by the linear combination x1 multiplied by the first column of A plus x2 multiplied by the second column of A all the way down to xn, this should say xn, multiplied by the nth column of A. And that's exactly what we see here. Here, these are the entry by entry definitions, but down on the bottom, we see that this is colon notation for the appropriate column. One of the things we're doing together is cultivating your ability to translate abstract mathematical concepts into viable computer code. To do that, we're going to do some analysis using our brain first. Remember, before we start coding, we have to fully understand what we're trying to do in those algorithms, which often involves pen and paper analysis. So, idea is we want to implement this in code, and to do that, we're going to produce an output vector, B, which is our desired output, that comes from multiplying a m by n matrix A by an n by 1 vector x. And again, we'll kind of just highlight the dimensions here. This has to have m rows and n columns. This has to have n rows and 1 columns. Those are given as input, and then B is our desired output, the thing that our algorithm produces. We've just done a recall to say that the matrix column vector multiplication via linear combinations definition is actually to scale each column of A by the corresponding individual entry of x. So the first column of A is scaled by the first entry of x, plus the second column of A scaled by the second entry of x, all the way down to the nth column of A, since A has n columns, scaled by the nth entry of x. This definition involves repeated column vector addition. Left-hand side of this addition is a column vector, the right-hand side is a column vector, and scalar column vector multiplication. So this is a scalar vector multiplication, this is a column vector addition, scalar vector multiplication, column vector addition, all the way down to the end there. Of course, one of the things that we can do is rewrite this using summation notation. In order to calculate our desired matrix column vector multiplication, we're going to sum up over the columns of A from k goes from 1 to n. Here I'm going to use k as an index because we're going through columns, where each time we sum, we're taking the corresponding entry of x and multiplying it by that column of k. Now, one of the things that I want to kind of highlight is anytime you see a summation like this in mathematics, this is an opportunity to translate math into code. Specifically, this use of sigma notation, this letter here, this capital sigma, that's a Greek letter called sigma. So summation notation, sigma notation, suggests that we're going to repeat the same operations a predetermined number of times. What operations are those? Well, we have a scalar vector multiplication and then a vector-vector addition done exactly n times. Anytime we're going to repeat the same type of operation a predetermined number of times, we might be thinking to ourselves, this is a perfect opportunity to use for loops. That's exactly what for loops are designed to do. Repeat the same type of operation a predetermined number of times. This gives us our first suggestion on an algorithm. In order to calculate A times X, we want to use a for loop. And then another kind of hint in using for loops is to use the following structure. First, we're going to initialize the for loop, and then we're going to run the loop to actually do this calculation. To initialize a loop, we can use a mathematical idea that is really, really simple. Specifically, if I want to calculate b equals a times x, I can always add a 0 vector to a times x, and it does nothing to the output of that calculation. So b is a times x is the same thing as saying as b equals 0 plus a times x. Of course, we have to do a little bit of analysis. Remember that a is an m by n. X is an n by 1, the inner dimensions must agree. Those dimensions cancel out, and the size of the output is going to be determined by the row size of A and the column size of X. So this would be an m by 1, which means if this is an addition, this 0 must also be an m by 1, which is something we keep in mind since this product is going to be an m by 1. And we can abstract away from that and think, you know what, let's think about this as just adding an m by 1 vector to our desired output, where we initialize the m by 1 vector to be 0. Because if we initialize it to be 0, then of course we're not changing the value that we desire, and we get the exact same thing out. And with that, we have our first of two techniques that allows us to translate the mathematical definition of a matrix column vector multiplication into a workable algorithm that we can code in MATLAB. And that trick is to initialize a vector y. In this case, we'll set that vector to be 0, and then use that as a starting point to enter our loop. The second trick that we're going to use is our memory saving technique. Specifically, in this case, what we're doing is we're defining a new vector b, and then using that to store the entries of y plus a times x. But in this case, the y is kind of a placeholder that we use to initialize. We could, of course, overwrite the values previously stored in y with the new values that we desire, and then y would be the storage for this b. And with that chain of reasoning under our belt, we now have a functional method to translate the definition on the left into the pseudocode on the right. We start with an initialization where we set the vector y equal to zeros. Those zeros are the row size of the matrix A. Then we run through n iterations of our loop, running over the column, so k goes from 1 to n. The next version of y is going to be the previous version plus the kth entry of x multiplied by the kth column of A. We're now ready to try to implement this using MATLAB code. Over here, I'm going to start a new script file so I can repeat these operations multiple times. Let's go ahead and save. I'm going to go to my desktop, and this is going to be actually a BLAS2 library, Basic Linear Algebra Subprogram Level 2. And I'm going to call this a sandbox because we're not actually coding a library. What we're doing is playing around with the different algorithms we're going to use to eventually develop the library. In this case, this is going to be matrix column vector multiplication via linear combinations. I'm going to call this my sandbox since all I'm doing is playing in the sand. I'm not constructing a building that I'm going to share with other people. The next thing we're going to do is determine a matrix example that we might want to use. Here is an example from a previous video. I'll link it up in the right-hand side that you can click on that shows a 4x3 matrix and a 3x1 vector. I'm going to reuse that since we've already done that analysis by hand. And here we go again. I just input these matrices into MATLAB. Let me go ahead and comment to say, let's create test data. I'm going to go ahead and clear memory and also clear the screen, remembering I'm not going to share this with other people because I don't want to do that for them if they use my code. This is literally just a sandbox. Okay, so now I have A and I have X. Let me go ahead and produce YMAT, which is going to be A times X. So this is going to be MATLAB output to verify my algorithm. So now I know what I'm searching for. Let me run this thing. Got to change folders and check this out. YMAT. Okay, so this is the vector that I want to produce via my algorithm. So let's go ahead and do our algorithm now. So the first thing we're going to do is initialize our code. So kind of a few different ways to do this. Maybe we want to set m comma n to be equal to the size of whatever matrix A we're going to have. And then what we're going to do is initialize y equals zeros, in our case m comma 1, so the same number of rows of A. So this is initialize our output vector. And then we're going to run our for loop. So for going over the column, so I like to use k to index columns and i's to index rows. So this is going to go from, k goes from 1 to n. And then we said that the next version of y is going to be the previous version of y plus the corresponding entry of x multiplied by the kth column, right? So in the kth iteration, I'm going to multiply the kth entry of x by the kth column of A and add that to the previous one. In the first case, we know that the previous value of y is 0. So when I kick into that first loop iteration, this is going to be 0 plus x1 times A1, the first column of A, which is exactly what I want because 0 does nothing. So I end that. And then at the end of this loop, the claim is that this is the vector that I should get out. Let's go ahead and run it. So now my YMAT, that's that one, and my Y, check it out. If we look at the difference between those two, YMAT minus Y, the two vectors should be the same if and only if MATLAB produces the same output that we produce. And that's exactly what we see. Those are zeros. With that, notice we have our first version of our matrix column vector multiplication algorithm. Let's analyze this piece by piece, thinking about that 4x3 example and really getting a sense of what's happening here. Here we are with a visual representation of the algorithm that we've implemented. On the right-hand side, we have our key math operation, which is to add an initial vector to the product A times X. On the left-hand side here, we see the pseudocode for that. We're going to update Y as the previous version of Y plus the kth entry of X multiplied by the kth column of A. And we do that from K goes from 1 to N, where N is the number of columns in A. And then the visual progression is going to let us know what's actually happening to our vector Y as we work here. As we initialize this, prior to entering this for loop, we've set the values of Y to be predetermined. In our case, we set those values of Y to be 0. Later, what we'll see is they don't actually have to be 0. This could be any affine transformation. In other words, Y could be non-zero if we wanted it. 0 just guarantees that the output that we have is A times X with no additional information. That being said, we initialize those values to be a 4x1 in our case. Here, A is any 4x3 matrix, and then X is any 3x1 vector. And the claim that we were going to do is we're going to update Y with the corresponding entries piece by piece. So after we've initialized, we have all 3 of these pieces of information in memory. Then we drop into our loop iteration. In our first loop iteration, where K is equal to 1, what we do is we update the previous version of Y, that's the initial version, with X times the first column of A, right? And that's exactly what we see, X times the first column of A. This happens in an entire block, so we're actually updating the entire vector all at once. Once we get that done, we go to the next loop iteration where K is 2. We drop over to the second column of A. We multiply that entire second column by the second entry of X, and then we add that to the previous version of Y, which included both the initial version plus the first column. Then we go to our third iteration. We drop into the third column of A. We multiply that by the third scalar entry of X, and we add that to the previous version of Y. Once we finish that iteration of the loop, we kick out, and we've actually ended it. A is untouched in memory, X is untouched in memory, and Y now stores the exact operation that we wanted. It's at this moment that I want to rub my hands together and ask you a question. Do you see something familiar with the key operation inside this loop? In particular, I'm going to call out some interesting structures here. This operation is setting a vector to be equal to a vector plus a scalar times a vector. Or another way to say that is scalar alpha times X plus Y. That is exactly an axpy operation. Scalar times a vector plus a vector. Let's remember this from a previous video. We said that an axpy operation on column vectors is an operation where we start with a scalar, alpha. In this case, the kth entry of X is playing the role of alpha. We multiply that scalar by a vector, X. In this case, the entire kth column is playing the role of X. So the kth column of A is our vector. So scalar times a vector. And then we add that scalar vector multiplied to another vector Y. Here, the vector Y is playing the role of the vector that we're adding, and that's what we call an axpy operation. But remember, we have an algorithm to implement axpy operations. Specifically, if we want to implement this axpy operation, where the vectors X and Y are m by 1, what we do is we overwrite the previous value of Y with the new value of Y plus alpha times the ith entry of X, meaning that we travel down the rows of X, multiplying each entry of X by the desired scalar, and then adding that to the corresponding entry of Y. But this immediately implies that we can take this inner loop and replace it. Instead of thinking about this as vector information, we could think about it as scalar information. In other words, right now, the way that this algorithm is written is BLAS level 2. It's done in terms of vectors. We're not actually getting down to the entry by entry definition. We're keeping it general in terms of vectors. But if we wanted to go down to the lowest level, we could replace this with the corresponding axpy. So let's go ahead and do that. We're going to actually leave this code because it's working well. So this is going to be BLAS level 2, vector sized updates. And then what we're going to do is copy and paste. Let's go ahead and comment all of that out since we don't need it anymore. we'll paste again, and we'll actually go down to BLOS level 1 where we're thinking about this entire operation, looking at this as entry by entry updates. And what we're going to do is replace that inner operation with the for loop version of the axpy. In this case, we're going to run over the rows. Well, how many rows are there? We start at row 1 and we go down to row m, since that's the size of A. And we have to think for a minute. In this situation, this is our axpy algorithm, but this is going to be the kth entry of x, and this is going to run down the kth column. So in other words, the ith value of y is going to be the last ith value of y plus the kth entry of x, since that's the scalar that we want. And then we're going to travel down the kth column of A. So here it's the kth column. Each entry is going to be in the ith position. And the claim is that this now should be our axpy operation for the matrix vector multiplication. Let's go ahead and run this. So now let's delete and run. The claim that we want to check is whether or not our ymat is the same thing. So remember, ymat was going to be this. Let's check y. We'll check that out. Now all of a sudden we have a matrix column vector operation that produces the exact product that we want, but it does it down at the entry level, which means we've actually coded two separate versions of matrix column vector multiplication. One of those versions stayed in vector form. The other version went all the way down into scalar form, relying on a previous implementation of an axpy algorithm. So actually, if we were really excited about this, we could use an axpy BLOS level 1 operation function to run this inner loop. Doesn't really matter which we want to do. The point of this is actually to show multiple representations of the same idea. Y'all know my steez by this point. Every time we're doing something new in math, I like to have multiple representations to figure out what I'm doing. Let's visualize what's happening with this nested for loop. We have an outer loop in terms of the columns and an inner loop in terms of the rows. Let's visualize what the computer is doing as we work through those loops. In this visual, remember that the math operation that we're calculating is up here. So we're taking a vector y and adding that to a matrix times our column vector. That's done with two loops. Our outer loop k runs through the columns of A. Our inner loop I runs through the rows of these. And the ith value of y is going to get the previous value plus x sub k times the I kth entry of A. Here, when we initialize, we start with a vector y stored in memory. We start with a matrix A and a vector x. And after we have those stored in memory, then we go through our outer loop, set that equal to k equals 1. And then we kick into our inner loop, set that equal to I equals 1, which means first we multiply the first entry of x by the first entry of A, and then add that to the previous value of y. Then we progress down along the rows. So we go down to the next entry of A, multiply it by that first value. Then we go down again. We multiply the third entry of A by the first value and update. So at the end of our first iteration, here I is 4 and k is 1. In other words, I is equal to the number of rows of m. Notice that we get that linear combination of the first column of A multiplied by the scalar x1 and added to the previous vector y. Then we update our outer loop. So now we go from the first column to the second column. Here, we take that first entry in the second column multiplied by the second value in x, add that to the previous value that was stored here. We then progress down those rows for that inner loop that we see. That's exactly what we're doing. So we go down to the second, the third, the fourth, each time overwriting the previous value with the scalar multiplied by the corresponding value of A. Now we get back to the end of our inner loop, since m in this case is 4. In other words, the number of rows is 4. Then we kick out to the outer loop. We update that outer value. We go to the first one, multiply that by the third scalar in the vector x. We add that to the previous value in y. Then we traverse down all the way through updating. Then after this, we are at the end of our inner loop. We're at the end of our outer loop. So we kick out, and notice the vector that's stored in y is the exact operation that we want. In this entry by entry version, notice that we're thinking about A in terms of columns. So literally what we did is we partitioned A into columns. We traveled down this column first, multiplied it by the scalar. Once we were done with that, we added the next column multiplied by the scalar. Then we go to the third column multiplied by the scalar. We update y accordingly. And with that, we've translated our abstract mathematical definition, where we take a matrix and multiply on the right-hand side by a column vector, into an algorithm to implement that both at the vector level and the scalar level, and then turn that into MATLAB syntax to realize that implementation and actually test and verify that the code that we produce runs as we expect. That leads me to my community challenge for this video. Community challenge is actually getting us ready for a next set of videos. What would happen if we switch the loops? Specifically, what if we put the for loop in terms of the rows on the outside and the for loop in terms of the columns on the inside? How does that affect how we progress through our matrix, and what operations would be used in those cases? You can go ahead and put those comments in below. We're going to do a whole set of videos on that, and we're going to talk about the different representations and different ideas that come from switching loops around. There's a whole analysis of which of these are faster. For now, I just want to get the mental juices flowing and get you excited about our next exploration. Thank you so much for your attention, y'all, and I'll see you in the next video.